Okay, are there any questions before we get started? Okay, no questions, very good, so we just move ahead then. So we talked about current, voltage, and power in the last lecture. And then we also talked about KVL and KCL. KVL and KCL. Okay. KVL is Kirchhoff's voltage law, and KCL is Kirchhoff's current law. And they found that Kirchhoff is usually spelled this way, with 2 H. Okay, and his first name is Gustav. He was a Prussian, but did most of his work when he was in Germany, maybe around 1850s or so. And most of his work was done around that period in history. Okay, and we learned about KVL. KVL is just a statement that the potential drop around a loop is always equal to 0. Very much like what you have in the gravitational field. So if you have a voltage source, and if you have resistors, maybe we can just talk about resistors first. And all of us know what resistors are. R1, R2, R3. And if this gives out a current I, there will be a potential drop across this resistor as the current flows from left to right, and then there will be a potential drop across this resistor as well if the current flows in this direction. Okay, and if we call this voltage drop, say V1, and this voltage drop V3, and if we go on the outer loop, this is the voltage rise, this is our voltage drop, this is a voltage rise, and what it says is that this voltage rise must be equal to V1 plus V3 as we go on this loop. Okay, this is KCL. We can also go on a smaller loop if you want and call this, say, V2. Okay, then you also have V is equal to V1 plus V2. These are KCL. Okay, KVL, you're right, KVL. And then KCL is just the fact that given any node, the current entering the node must be equal to the current leaving the node. For instance, if I call this I1, this is I3, and this current is I2, then it must be the fact that I1 must be equal to I2 plus I3. The current entering the node must be equal to the sum of the two currents leaving the node. And that node can be over here as well. Okay, but this is trivial. It just says that the current flowing here is equal to the current flowing there. You can also set up KCL at this node as well. Okay, and so that is very similar to that node, and so on. And so these are the essence of KCL, which is due to charge conservation. KVL is very much like the potential energy of the gravitational field of the Earth, but that potential energy comes from the electric field generated by a source, a voltage source like a battery. And it creates potential differences around the loop, and that potential differences always add up to 0 as you go around the loop. Okay, just like in the gravitational field. Okay, so today we're going to do something new. We're going to talk about ideal current elements and talk about BI relationship. For ideal current elements. Okay. The first one that we like to talk about is a resistor. I'm sure that you have come across resistors before in other courses, like your Physics 212 and maybe your ECE 110. Okay. A resistor is simply a piece of device where if you have a voltage drop across this device, okay, there would be a current flow, and that voltage drop is equal to the current flow times the resistor's value. Okay, that is just so what the resistor is, and this is simple Ohm's law. Okay, Ohm's law is just a thing, and hence resistors are measured in the units of ohms. Okay, so you can think of it as 1 ohm, 2 ohms, 3 ohms. This is measured in terms of amperes. This is measured in terms of voltage. So resistors has the dimensions of voltage over amperes, if you want to think of it that way. But it's given its own unit in honor of this person, Mr. Ohm. Mr. Ohm probably did a lot of work on resistors in the past. And what is a resistor made of that causes the current to be proportional to the applied voltage? It essentially consists of a device where current can flow, not like a conductor, but a device where current flows with some obstruction. Okay, so there's some kind of obstruction going on and does not allow current to flow freely. And this obstruction is provided by the fact that most materials are not made of conductors, but made of crystal lattice. Okay, you can think of most materials have crystal lattice, and crystal lattice are made from nuclei of atoms. They arrange themselves together to form lattices. And as the electron, current flow is not due to positive charges, as we mentioned before. Current flows are due to the flow of electrons. Okay, as the electrons try to move through this thing, they will collide with the lattice in a zigzag fashion. They never travel in a straight path. You'll move around in this kind of random walk fashion because of this collision. And there are many lattices and many nuclei points that the electron will collide with. So the electron does not move freely from A to B. And hence, the lattices provide obstruction and hence resistance to the flow of the current. That's what it means. Okay? And hence, the current is linearly proportional to the voltage in the sense that that current flow is VR over R. The larger the applied voltage is proportional to the potential drop, and hence some kind of internal electric field. Some internal electric field will be generated in this resistor. The electric field is what pushes the electrons around. And in this picture, to be correct, I should draw that the electric field should point in this direction. Okay, and to make this picture correct, I should say that this is at a higher potential than this. The electric field always points from the region of high potential to the region of low potential. But electrons move in the opposite direction, giving rise to a positive current flow. And we electrical engineers think of currents as being due to positive charges. That concept is wrong, but it's something that we have to accept because we are all electrical engineers. Okay? So that is the thing behind resistors. Because of this zigzag flow, okay, so we often represent a resistor with this zigzag line, implying that the current does not flow freely in a straight line through these resistors. Okay, and the power dissipated by a resistor is equal to the voltage times the current flowing through it, and you can express everything in terms of current. V is IR. Okay, let me say V is IR. So this current is I square R, and hence the power loss. This is also called the power absorbed. or power loss due to a resistor, that loss is proportional to I squared R. And as an electrical engineer, you will always hear the term I squared R loss. Okay, what is I squared R loss? That means resistor loss. Nobody talks about IR loss. Okay, it's always I squared R loss because of this formula. Resistors are no good, but they cannot be avoided. But sometimes you need them. You need them to give you the proper voltage drop across another device that you're using. For instance, if you have a voltage source here, and if this voltage source is too high, and if you connect it directly to your device, your device may not be able to withstand the voltage of this voltage source. Okay, it might get fried, depending on what kind of device you have. Okay, in order to protect this device, you can put the resistor here. Then there will be a voltage drop across the resistor, and then there will be a voltage drop across the device, and V will be equal to VR plus VD due to Kirchhoff's voltage law, and the voltage drop that you have across the device will be smaller. And if this device has a resistance to it, the current flow through the device will be given by VD over R of the device. Say it has an internal resistance to it. And you can control the current flowing through your device, okay, by adjusting what resistors you should connect in series with this device. And you can also control the I squared R loss, okay. Then the power dissipated on your device, if it is a resistor, will be I squared R. And by controlling this voltage drop and also the current, you can control the I squared R loss, and you do not want your device to be fried. And if I squared R loss is too big, the device will be fried. Okay? So this is one use of the resistor. And then oftentimes you have this, are there any questions so far as to what a resistor is? I guess you don't have any questions. Then oftentimes you have symbols for open circuit as well. Okay, this is usually called an open circuit in electrical engineering. And then you have a symbol for short circuit, which is just usually a straight line across. Okay. So there will be a voltage drop across an open circuit, and usually there will be a current flow across a short circuit. That is usually called a short circuit current. This is usually called an open circuit voltage. Okay. This happens if the resistor is infinitely large. If this resistor is made to be infinitely large in value, no current can flow through it. It very much behaves like this. And if this resistor is made to be zero, then it behaves like a conductor. Current can flow very easily. There will be no voltage drop across this resistor, and then it behaves like this. Okay, the V drop is zero. Here, I is equal to zero for this picture over here, open circuit and short circuit. Those are the two things that you should know. Okay, are there any questions? If not, let's move on and see what we can say. Well, I'd like to talk about voltage sources next. And I'd like to talk about voltage sources that are independent. Okay, or independent voltage sources. And usually we denote that with a symbol that looks like this. And that is a voltage source. You can also see other symbols in the literature. Sometimes you see a battery. That is also a voltage source. This will be positive, negative. And you can see a stack of them sometimes, depending on how long or how many batteries you want to draw, but they're the same thing. Okay? And sometimes you have voltage sources with this symbol on it. This means an AC voltage source. AC stands for, what does it stand for? Alternating current. Very good. AC stands for alternating current or alternating current. Okay, those are the kind of voltage sources you can have. And of course, when you have a voltage source and hook to a resistor, then you can do calculations very easily with it. Say this is a 4-volt voltage source hooked to an 8-ohm resistor. Tell me what current should be flowing through this or out of this voltage source. What is I over here on what you have just learned? I is V over R, right? So it's half an amp, 0.5 amp. Okay, that is what you should have. And then, of course, if you have two resistors in series, it's like sum of the resistors together into one. Okay, say if you have a 3-ohm resistor and then 2-ohm resistors together, you have a voltage source. Say if this is 2 ohms, this is 3 ohms, and then you have a 4-volt voltage source over here. Okay, and then let's assume that you do not know what the current is. Okay, you do not know what the current is. Then you know that the voltage drop across the first resistor plus the voltage drop across the second resistor must add up to the voltage rise as this current is flowing. The voltage rise due to the voltage source. So voltage source is like the pulley system in the potential energy of the gravitational field, like the Archimedean screw. Okay, you probably this is a navigation, not navigation system, an irrigation system used in the ancient time to raise water from one part of a pool or a well to another part. By turning this screw, water gradually rises from the bottom of the well to the top and then gets poured out to another part of the field. Okay, there are similar devices in China too, but in the West it's known as the Archimedean screw. Okay, it raises the water from a low potential energy region to high potential energy region, drop in the well, and because the water now has high potential energy, they can be used to do other works. Okay, so the battery, the voltage source is something like that, like an Archimedean screw. Okay, that you use to do work with. And this is, of course, can be generated by a generator, like a rotating machinery, or it can be obtained from chemistry using a voltaic cell. And using some chemical reaction, you can cause the energy, the electron to go from here to there, even though the potential energy is higher. Okay, by using a chemical reaction. So if I ask you that the voltage drop across resistor 2 plus voltage drop across resistor 3 must be equal to the total voltage rise, so I immediately get the I times 2 plus I times 3, which is V3, this is V2, this is V3, that must be equal to 4 volts. Okay? And immediately I can solve for I is equal to 4 over 5 amp. Okay, just take this outside, factor out my I, and then solve my I to be 4 amps. And you can see that putting two resistors in series is like adding them up together. I could have also solved this equation and say that this is in total like a resistor of 5 ohms. Okay? And then the voltage drop across these two resistors is just I times 5 is equal to 4. And from this immediately I get I is equal to 4 over 5 amps. So there are two ways of solving this problem. Using the knowledge that when resistors are in series, you add their resistance and consolidate them into one resistor, or you can go to this KVL thing and write down the equation and solve for them. Either way is fine. And if you do have another source over here, like maybe 2 volts, you will have to factor in the effect of this source by the fact that when you are going from here to here, there is a voltage drop in this direction. Okay, the current flow that you have will be different now because you have added this source. This source actually is trying to drive the current in the opposite direction compared to this source. Okay, this source is driving the current in this direction, but this other voltage source tries to drive the current in the opposite direction. Would the current be smaller or bigger according to your intuition if I add a voltage source over there? Smaller, right? Because the net voltage that the whole loop has is smaller. Okay, you don't even have to solve the problem. So you can do some, what we engineers call sanity check. Okay, sanity check, but make sure that the results do make sense before you write it down in your exam. Okay, do some sanity check. Just let me write it down. Okay, in addition to voltage sources, you also have current sources. Current sources are represented by a symbol such as this. Okay. Voltage sources are represented by this symbol. And you can say that voltage sources has this property, that this value is immutable or does not change. Okay, this value of the voltage source does not change irrespective of what you hook to this voltage source. You can add a resistor, you can add resistors of any ohmage. This value does not change. That is a property of an ideal voltage source. Of course, in real life, there's no such a voltage source. This is idealization. Okay? Similarly, a current source has the property that irrespective of what you add outside, a resistor, maybe another resistor outside, this current flow is going to be kept constant. This is the property of a current source. Ideal current source. Okay, there's no such thing in real life. We can get close to it but in our engineering design, but there's no ideal current source. So this is ideal. This is also ideal. And this current is immutable. Okay? Those are the two things you have to notice. And so, using this idealization, then we can say that if we have a current source of 3 amperes, it will remain to be 3 amperes irrespective of what you do to the outside world. Okay, say if you have a 5 ohm resistor, find the voltage drop across the resistor. This is a very simple homework, and you wish it's on your homework or on the exam, right? So that voltage drop is equal to 15 volts. Okay? So if you add a big resistor, you get the larger voltage drop. That is what an ideal current source is. There's no such thing in real life, but that is what you have to assume. Okay? And you can have other examples in the textbooks. The textbook has an example, which I like to write down, that you have an ideal current source, 4 amps, and then you have 2 resistors hooked in parallel. One amp going that way, and then you have 2 ohms, and then you have 1 ohm. Okay, by the way, this is a symbol for ohm. It follows from a Greek letter. And how you read this in the Greek letter is omega, okay, not ohms. Okay, this is the Greek letter for omega. This is a capitalized version, and you probably have seen the other version, the lowercase version. This is the uppercase version, this is the lowercase version. And we use that for a symbol for ohms. Okay, oftentimes we just do that. And now I ask you to find the voltage drop across this one. Okay, how would you do that? Okay, now you know that the current that flows here must be 1 amp. Okay, the current that flows here must be 4 amps. Okay, I do not know what these two currents are, I1 and I2. I can solve for them using Kirchhoff current law and Kirchhoff voltage law. Because this is 1 amp, this is I2 coming down. What do you think is the current flowing here? It will be 1 amp plus I2, right? So the current flowing in that arm is I2 plus 1 amp. Okay, that is the current flowing in that arm. Because this current is flowing in that arm, what is this current flowing down here? I1 plus I2 plus 1, which is the total current leaving the node, must be equal to 4 amps. Okay, if I apply KCL at this node. I first apply KCL over here, KCL over there. And then I have this requirement that I1 times 2 must be equal to V. Since this is the same voltage drop for both resistors, must be 1 times I2. So you have two equations and two unknowns. Okay, two equations being that I1 must be equal to half I2. Okay, and then you can substitute into the first equation, or you can say I2 is 2I1, doesn't matter. So you have 3I1 plus 1 is equal to 4, which implies that I1 is equal to 3 over 3, okay, which is 1 amp. Okay, I1 is 1 amp, and then you can figure out what I2 is. I2 is equal to 2 amps. Okay, so it works out fine. If this is 1 amp over here, it creates a voltage drop of 2 volts. If this is 2 amps over here, it creates a voltage drop of 2 volts. Okay, what other ways could we have solved this problem? By reducing it to a simpler circuit. Yes?
You can use parallel resistors.
Right, right, very good. You can connect these two in parallel, just like the fact that you can connect these two in series and consolidate these two resistors into one and reduce this to a simpler circuit that will look something like this. And R parallel is equal to, I'm sure that you have learned this formula before, right, from some other courses. 1 over R1 plus 1 over R2. Okay, when you connect two resistors in parallel, you get a new resistor and you can work with the reduced form of the circuit instead of working with the more complicated circuits. Okay. I think we'll derive this formula, or maybe it has already been derived for you, but you can go through KCL and KVL and derive it yourself if you want to. Okay. This is also called the geometric means. Okay, the geometric means of two resistors. So parallel connections are giving rise to the geometric means of two resistors. And geometric means of two resistors is always higher or lower than the sum. It's always higher than or lower than the individual resistors. Which one is the true state? Lower. Okay, if R1 and R2 connected in parallel, the geometric means of the parallel connection is always lower than the lowest resistor in the circuit. You can do a sanity check on that too, right? It's like traffic jam, right? If you have one bridge for the traffic to cross the river, okay, you have this certain amount of traffic jam. If I have two bridges to cross the river, the throughput through these two bridges has to be higher than either if I just one of the two bridges alone. This is just a simple sanity check. Okay, so the geometric means of two resistors connected in parallel must be smaller than them by themselves, by itself, okay, each by itself. Okay, So let's see what we have now. The next thing I'd like to talk about is the dependent sources. These are called independent sources because they stand alone. Nothing can change them. They're immutable. You try your best to change them, they won't change. Okay, they're very stubborn. Okay, but then there are other kinds of sources that depend on other things, and those are called dependent sources. Like they're usually represented by a diamond symbol. Okay, that Vs would be a voltage source. There would be some current flowing due to this, not necessarily I sub s, but this Vs is linearly proportional to some voltage somewhere else. Okay, it's not controlled by you. It depends on the voltage somewhere else. Maybe in a very complicated circuit, some part of the circuit there's a Vx there, and this voltage source depends on that voltage drop. Okay, this actually is very important for modeling transistors. Transistors are very complicated devices. It cannot be modeled just by R, L, C, and simple dependent or independent sources. You have to bring in dependent sources like this to model how a transistor works. Okay, you will learn about that in ECE 1. 310? 342? Okay, 342. Okay, you will learn about those things later on after this course. Okay, but this is just a precursor to the fact that when you have dependent sources, you can model more things, including transistors. Or this Vs can also be proportional to some current somewhere. Not necessarily have to be some voltage somewhere. It can be linearly proportional to some voltage. Okay, and then you have dependent current sources, denoted by this symbol over here, with an arrow in between, and then it will have a current. Okay, that current is linearly proportional to some voltage somewhere else in the circuit. I don't know where it is right now. It can be any place, or it can be linearly proportional to some current somewhere. Okay, these are all kind of statements over here. Okay, when it's dependent on the voltage somewhere else, this is called voltage control voltage source. When it's dependent on the current somewhere else, this is called current control voltage source. And similarly for this will be voltage control current source, current control current source. Okay, so they're either voltage or current control. So they're not stubborn. You have to listen to other people. Okay, they're not stubborn like some students. Okay, they have to listen to other people. So these are the control sources. So let's give an example of how this class of problems should be solved. Say if I have an independent voltage source over here, and then I have a resistor, 2 ohms resistor, and then another 2 ohm resistor over here. And then I have a voltage control current source. And that current source, I, S is 2Vx. Okay, it depends on the voltage drop across this resistor. Okay, how do I solve this problem? That I have a current source, its value depends on the voltage drop across the 2 ohm resistor indicated there. How do I solve this problem? Okay, so I set up Kirchhoff current law and Kirchhoff voltage law. Okay, so if I look at this now, this current here must be, IS must be 2Vx over here, right? And then this current over here must be Vx, let me say I3. Okay, I3 must be Vx over 2 ohms. Okay, so then I would have this voltage drop over here. Okay, this voltage drop over here must be equal to, what is the voltage drop across this resistor from Kirchhoff voltage law? Must be 4 volts minus Vx, right? So this must be 4 volts minus Vx. That is the voltage drop across that resistor. Let me write a capital V. 4 minus V. Okay, that is the voltage drop across that. And hence the current flow is just 4 minus Vx over 2. Okay, that must be equal to Is plus I3. Okay, minus I3, sorry. Is minus I3. No. It's minus Is plus I3. Okay, that current flow through this resistor, which is this voltage drop, divided by the resistance of that resistor, must be equal to the current that are coming in and leaving that node. And if you set up Kirchhoff current law at this node, this is the first equation you get. And Is is equal to 2Vx. So I can say that this is I3 minus 2Vx. Okay, so this equation has one unknown and two unknowns, I suppose. I3 is not known yet. Okay, so this is Kirchhoff current law. And then I know that I3 times 2 ohms. Okay, I3 times 2 must be equal to Vx. Okay, so two equations and two unknowns, you can solve for them. Okay, you can substitute in Vx for I3, and then you can solve the two equations, you obtain your Vx, and so on. Do you want me to